All right, let's get started. Yes, once again, sorry for the delay. Hopefully you guys can see me. Hopefully you guys can hear me. Let's actually continue with where we left off. And yeah, originally, so just to cover some things that have been going on in the chat. Originally, Kevin, okay, we'll see. Originally, Kevin made a joke, now I forgot what I was gonna say. So yeah, originally you would have also not had class today and started on Monday, but the way things were set up, it just by how everything was shuffled around, that would actually put you guys again behind the RS2 section, which I have my class with them on Thursday, tomorrow. So with this, you're both going to be at the same point week by week. To also follow up on the testing situation, again, the administration has not made up its mind. I'm just as frustrated as you guys are, and I'm moving forward with the original plan that I wanted to do. So I'm going to go, I have to schedule a workshop, which I believe the earliest to do that is Friday. Make sure I can get the technology to work out, and I'll get you guys back. I'll hit you guys back by early the following week, and we'll try to set something up. In terms of the final, I don't know, but in terms of in-class exams, I'm just going to do my own thing because they're really dragging their feet here. That being said, yes, so I still want to give you guys 2 exams. At the very minimum, it will be like one of the comments suggested. It will be something like through Pearson, which is timed. But I'll probably also have some sort of proctoring going on as well. That is the hope. And yeah, it'll just be you do it at home and you scan it and whatever. Just kind of go through that system. But both I have to, yeah, make sure that from the technical side of things, I will be able to set things up from this side. So yeah, I'm just going to move forward because we only have a few weeks, 3 weeks or so until the end of the semester, and I'm tired of waiting on them to make up their minds. So we're going to move forward. That being said, we are going to, it's a little more than 3 weeks. It's about, because our last class is about May 14th, 15th, somewhere around there. Yeah. So anyway, yeah, I'm going to set up my own thing and we're going to move on with that. That being said, let me share OneNote with you guys. And this is what we'll be talking about today. So let me make sure I can see the chat here in case anyone wants to say something. Yeah, I'll send you guys, yeah, last day of classes is May 14th. In terms of what we're doing for testing, I'm attending the workshop on Friday, and so by Monday, I'll give you guys specific instructions on how we're moving forward with the tests. And the school can do whatever it wants to do with the final, but by Monday, I'll get you guys some testing stuff. So the rough timeline will be, by Monday, I'll let you guys know exactly what we're doing for tests, which means then I'd also by Monday give you guys a practice test to do. And so the test 1 will be like a week after that point, and then test 2 will be around 2 to 3 more weeks after that point. And so, yeah, because the second test is going to be roughly the last day of class. That's after you reviewed everything. So that's the rough timeline there. So what I'm going to do also is I'm going to stop sharing my video because I've noticed that sometimes that causes technical issues, and you guys just have to read. You don't really have to see me. So I will stop sharing video at this point, and we will, yeah, in terms of the final schedule, it'll be a few days after the last day of class. But by then, I think you guys will be ready for it. I don't anticipate there should be any trouble. Because when you're studying for test 1 and test 2, you are studying for the final. It's essentially going to be like a combination of the 2 tests. So it'll just be one long marathon here, and you guys should be okay. I am only writing the final for the GH section. For the RS2 section, no. But yeah, like I said, it's been crazy times, and yes, I know it's very frustrating because so many things are up in the air, and so I'll definitely, whether I'm writing tests or I'm giving you a final for someone else, I am definitely going to make things fair. I'm not gonna make them harder than the tests that I would have given you guys in person. I'll probably even make them slightly easier because I want to give you guys the best shot that you can have. And I really want, I have no intention of making this harder than it has to be. I'd love to give everybody an A. I'd love for you all to learn all these cool things and just continue to move forward with our lives and hopefully return to some sort of normalcy. So the topics for exam 1, we've already covered it. It would be everything up to series, so right before parametric equations. So that would be exam 1. So integration techniques and all that stuff with series and Taylor series would be exam 1. Exam 2 is going to pick up with everything after that. So parametric equations, polar coordinates, not including the graphing and calculus part, and then the 3D stuff, which we're going to start today. And since we're just starting 3D, it's a whole new ball game. We're going to start with the basics. Really, the last leg of the class is going to be actually easier than the first leg. So some of you really have to brush up on your integration in series. That being said, the second leg of the class should be a lot easier because when we're talking about parametric equations, polar coordinates, and the 3D stuff, we're not going really deep into them. We're really kind of just introducing them, teaching you the basics, how to basically navigate through them and all that good stuff. So what we're doing now shouldn't be too bad, but it's going to require a new perspective. We are, as you can see, going to cover the 3D coordinate system. Now the title of this section is called the 3-dimensional coordinate system, as you can see here. But it really only covers one coordinate system. Yeah, as far as David is concerned, I'll probably hold a review, but I'll have to work out the schedule here. But yeah. I am sharing OneNote, but I'm not sharing my video. So if you can't see me, that is by design. I just want to minimize all the technical things. You can't see OneNote? Okay. So, yeah, let's actually begin. So again, we're going to do just a small intro here to the 3D system. It's called the 3D coordinate systems, plural, but we're really only going to talk about one. We're going to talk about the rectangular coordinate system in 3 dimensions. Okay, so as I mentioned here, it's really exciting stuff. We are going to learn how to navigate 3D space. Just in case I have a slip. Okay, welcome back, Kevin. Just in case I have a slip of the tongue, I want you to know that 3D space, I'll often refer to it as 3 space or R3. And in general, an n-dimensional space we can call n space. And if we are specifically thinking of the rectangular coordinate system, which we'll talk about, people usually refer to this as the Euclidean n space. So we can talk about the Euclidean 4 space or the Euclidean 7 space. Then you're talking about a 7-dimensional space. We are not going to go beyond 3 dimensions, however. And because you know most things in 2D, I'm going to really kind of emphasize 3D in this lecture, but I'll be comparing it to 2D, hopefully to illustrate what's going on. So we already know how to locate points in the 2D with the rectangular coordinate system. So the idea was, so you had X and Y, and if we wanted to locate the point, say 1, 2, what we did was we found 1 on the X, we found 2 on the Y, and we created a rectangle, and that was the point 1, 2. And so essentially in 3D, we want to do exactly the same thing, except now we have a third component to worry about. So there's an X-axis, a Y-axis, but what we're going to do is we're going to add a third axis. And how we illustrate this axis on paper is we sketch it like so, as you can see. We are going to have a vertical axis. Then we're going to have one stretching along here, and then we're going to have one going along there, and one going up. This is the x-axis as you guys are familiar with it, the y-axis as you're familiar with it, and we are throwing in a third axis at this point, which we would call the z-axis, of course. So this is how it would look, and you can sort of imagine, well, I have some nice illustrations for you down here, but we'll get to those. You can actually imagine that the negative x-axis will actually continue to go back that way. So this is the negative x-axis. The negative y-axis will continue to run in that way. And the negative z-axis will continue to go down. So if you look here, what I want you to kind of think of is like being in a room. Essentially, if you are standing in a room and you are facing a corner, then if you just imagine that the x-axis is running along the floor in the corner, where the corner here is what we call the origin. That's where your x coordinate is 0, your y coordinate is 0, and your z coordinate is 0. Emanating from that, going off on along the left wall, that is the positive x-axis, and going along the right wall, that is the positive y-axis, and running right up from the floor to the roof is the z-axis. The floor in that case, so if you're standing in a room facing the corner, the floor is what we call the xy plane. Notice that it is bounded, or I shouldn't say bounded, that the x and the y-axis lie in the xy plane. In the plane that the x and the z-axis lie, that creates another plane called the xz plane. That's essentially like your left wall in a room. The yz plane is the right wall in the room if you're facing the corner, right? So that's the important part. So if you are your man and your little guy, you're facing the corner. Yes, it's a very simple, quaint little room. But yeah, so you're a guy, you're in the room, you're facing the corner. Yeah, so the x-axis would be running here, the y-axis is running there. Now, normally what we're doing, what we've been doing before is like we're a little eyeball and we've always been looking down in the xy plane. So the x would look like it's from that perspective going off to the right, and the y would look like it's going up. But now we're going to pretend we're in a room, we're in 3D space, there's length, there's width, there's height. And we create this sort of space here. And essentially we would locate a point very similar to how we actually did it in rectangular coordinates before. So if we wanted to, for example, locate the point 1, 2, 3, notice here, and I'll talk a little bit more about this notation, that is your x coordinate, this is your y coordinate, this is your z coordinate. And essentially what you do is you run along the x, find the number 1, you run along the y, find the number 2. Now, just as you did before in rectangular coordinates, where you just kind of run these lines parallel to the axes, you can create You can create a point here that lives in the XY plane. And then what you do is you run up the Z, so to the point 3, and then you literally move this point up to a height of 3. And so what you'll do here, you'll notice what you would have created is you create, instead of a rectangle, you would essentially create a box where this, the point opposite the origin, that is going to be the point 1, 2, 3, right? And this is the point 1, 2, 0. Notice that this is where these Z, this is the point, the origin here is 0, 0, 0, right? Where all variables have the value 0. Okay, so that's kind of it. So the rectangular coordinate system means, again, we kind of create like this rectangle to find positions in this space. So you run along the X, you run along the Y, you can create this, then you run along the Z, and you lift the point up or down based on where it is. And so that's how you'd actually locate a point. And yeah, these guys here, the XZ plane, the YZ plane, and the XY plane, these are called the coordinate planes. I defined that somewhere down here. Now, if I typed out everything I'm saying in the notes here, so when I share the PDF with you guys, you'll be able to follow along. So I'm just going on here. So when you are standing in the room and you have this perspective like I'm describing here, we say that you are standing in what's called the first octant, okay? So assuming that the positive x-axis, positive y-axis, and positive z-axis are running in the way that you see, I want you to notice that you standing in the room, you would be standing in the first octant, because what you'll notice is that these planes here, the xz plane, the yz plane, and the xy plane, actually splits 3 space into 8 compartments. There's one, the room you'd be standing in. This is the first octant. In the first octant, all the x, y, and z values are all positive. But you can imagine that there's a room behind the right wall. That guy is known as the second octant. The room that's directly opposite to the room you're standing in is, yes, so the first octant is above the xy plane, but towards this view here. So the room that would be behind the left wall, that would be the fourth octant, and so on and so forth. So this is how the octants are actually labeled. So the first octant is where all the x, y, and z coordinates are positive. So you're here. If you move over to the other room, this means you're on the x where, yes, it's counterclockwise numbered. So if you go around the top, if you imagine you're in a 2-story building, you're on the top floor in this room, you're in the first octant. The room behind the right wall is going to be, if you're facing the origin, the room behind the right wall is going to be the second octant. The room directly ahead of you through the corner is going to be the third octant. The room behind the left wall is going to be the fourth octant. One floor below you, that is going to, in the same room that's directly below your room, is the fifth octant, and behind the right wall is the sixth. The seventh is going to be, of course, the room below the third, and so here I kind of described to you, we're going to have 2 exams and the final. So you might have missed that. So the first exam is going to cover everything up to the end of series. The second exam will cover everything after that. So parametric equations, polar coordinates, and all this 3D stuff. Okay. So these are how the octants. So you can split space into 8 different compartments with these planes here. The XZ plane, the YZ plane, and the Y plane. These guys are called the coordinate planes. One thing I also want you to notice is that we can actually describe them by equations. So the YZ plane, notice that in the YZ plane, your X is always 0. Any coordinate in this plane is going to have the coordinate 0, something, something. In the XZ plane, this has equation y equals 0. So this equation here has y equals 0. The xy plane, this is the has equation z equals 0. So everywhere on the floor here in the xy plane, that has z component 0. And so these equations would actually describe these planes, and they split space into 8 compartments that we call octants, not quadrants anymore. Quadrants was in 2D, but here we are going to talk about 3D, which gives us 8 spaces. And these are how they're numbered. Now, the most important one for you guys to know about is the first octant. A lot of times a problem is going to be described to you as being in the first octant. You won't hear these guys referred to in your typical calculus book very often, but that's how they are numbered, just an FYI. All right, so now in this coordinate system, we represent points by ordered triples, say A1, A2, A3, just as how I did up here, 1, 2, 3. That's just a 3 coordinate system. It's an ordered triple. The first component is always called, where are we? The first, each position here, each number is going to be a real number, like it could be a 1, a 2, and a 3. The first number is called the x coordinate. The second number is the y coordinate. The third component is called the z coordinate. And you can think of these as denoting a distance from the YZ, the XZ, and the XY plane respectively. So what do I mean by that? If I look at the point 1, 2, 3, and then I get this point. This is the point 1, 2, 3. Notice that it is 1 unit from the YZ plane. It is 2 units from the, sorry, this should be XZ plane. It is 2 units from the YZ plane. And it is 3 units from the XY plane. Right? So it's 3 units above. So this length here is 3. And of course, this length here is 2. And this length here is 1. So you can even think of these coordinates as talking about the distance away from each of the coordinate planes. Okay. Now let's actually talk about let's see if I mentioned everything I wanted to mention here. Okay, Euclidean n space, rectangular coordinate system, did that in 3D. The coordinate planes are these guys. They have equations x equals 0, y equals 0, z equals 0. They split space into 8 octants, quote unquote. And okay, right. Now let's talk about objects in 3D space, right? So we know about objects in 2D space. So we can have lines and curves and parabolas and all these kinds of geometrical objects and boxes, well, not boxes, rectangles, and we can fill them in and things of like that sort. We want to talk about similar objects in 3D space and how we would talk about them, right? Now we'll cover these more in future sections, but now I kind of just want to introduce the ideas to you. First, some simple ones. Let's look at the idea of a plane. So we looked at some planes before. These are the coordinate planes. These are like flat sheets. So a plane is a 2-dimensional object, which pretty much is flat. And I'll describe what flat means in a future lecture. But yeah, now these guys are the guys where x is 0, y equals 0, z equals 0. But what if I had other values like x equals some constant k, y equals k, or z equals k? What does that actually mean? Okay, so let's look at x equals 1, for example. Notice that if I'm talking about x equals 1, what I essentially want to do is describe all points where that the x coordinate is going to be 1. Now, notice that that will result in a plane that kind of runs parallel to the So notice that this is a plane that's parallel to the YZ plane, right? So it's just a flat sheet. You can just think of it as a flat sheet of paper. It's not curved, and it extends in all directions forever. I'm just drawing a slight sliver of it right here. And pretty much every coordinate in this is going to have the form 1, something, something. And so it's just going to be a flat thing. The line that you guys are used to seeing in the XY plane, this is the line x equals 1 in XY plane. And so there's just this flat sheet. And similarly, I can talk about the plane y equals -2. So for example, if I wanted to draw a small sketch of that. So of course, the negative y keeps going back that way. And so what I will do is I would find -2 on the y, and then there's going to be a plane that pretty much slices through that guy. And he is going to be parallel to the XZ plane. Right? So this guy is going to be parallel. But it passes through y equals -2 on the y-axis. I can also talk about another situation over here. So x, y. Now, just to mention, the orientation of these axes, relationally speaking, they always need to be in the same position, but you might not want to always draw them in this position. I've seen many different ways. I just want you to know that your textbook, whenever it's describing situations in 3-space, it is assuming that you have this orientation for the axes. So I know that sometimes people might draw things like they like the y and the x just as normal, and they might put the z down here, but we will not take this convention. We always will consider the x as going this way, the y is going that way, and the z is going up, just so you know. And so what we would do here is find the point where z equals 3, and then we can just think of there is a flat plane, a flat sheet, hovering in space. It is parallel to this guy's parallel to the xy plane. So it's just a flat sheet floating in space above the xy plane at a height of 3 units from the xy plane. Okay. Now, before we kind of move on, just to make sure, is everyone following so far? Can you, are you guys kind of visualizing things okay? Kind of? Okay. Well, we'll go over B. Okay, so so this is the y-axis, right? So the y goes off to the right here, right? So this is as y is increasing. This is the positive y-axis here. So like y equals 0, y equals 1, y equals 2, y equals 3, keeps going off. Negative y goes in the opposite direction. So that keeps going down, -1, -2, -3, so on, going that way. So find the point where y equals -2. I want all points. Yes, flat, infinitely thin, extending in all directions. So this actually extends all the way. And it's just a flat sheet so that it passes through the point y equals -2 on the y-axis, but it does so parallel to the xz plane, right? So yeah, this guy is flat. He's parallel to the xy plane, hovering above the xy plane. Right, this guy does not touch the xz plane, correct. So right, so it doesn't have any intersection points. Because, and you can know this, because the xz plane has equation y equals 0. So if your y can't be -2 and be 0 at the same time. So anything that actually goes into the, yes, similar with these guys will not touch any other coordinate planes other than the one that you see me striking through here. Because in the coordinate planes, one of these guys have to be 0. So if your x is 1, it means it will never be the case that x is 0. So this guy will never touch the yz plane. If y is -2, then it will never be the case that your y would be 0. So it'll never touch the xz plane. Here, if your z is 3, it will never be the case that your z is 0. So it will never touch the xy plane. It's literally parallel to them. It will always be 3 units away from the xy plane. Right? What about y equals x? What do you guys think that would look like? That's also a plane. What do you think that guy would look like? Okay, so now in 2D, if you're looking at y equals x, what it looks like is here's your x, here's your y, and it's just a line passing through the origin, pretty much going at 45 degrees. So you'll have the same kind of behavior here, but now you just have a plane. I want this to look parallel. But now essentially you'll just have a plane slicing through at a 45-degree angle, like so. It's going to be hard to actually visualize, but yeah, it would be running along. So this line here is this line here, running in both directions. And the plane contains the line. Okay. So it's kind of like these guys, but it's at an angle slicing through here. Maybe I can find a nice illustration here. Can you guys hear me? Oh, it's very strange. Okay. This is very strange. Hold on. Let me check something here. Yeah, no, I don't know what's going on. So I'm trying to find another illustration, but it's literally telling me that my internet isn't working, but somehow I'm still broadcasting to you guys. I don't know what's going on. Anyway, let's continue. Hopefully that's clear. Here's a question for you guys. What do you think this guy would look like? X squared plus y squared equals 1. What do you think that guy is? Right, now a cylinder. Now, normally, for all our lives up until this point, at least in two-dimensional mathematics, we think of this guy as a circle. It turns out that in 3 space, this actually describes a cylinder. Now, how would you figure out that this is a cylinder? Well, one, remember in 2D, this guy describes a circle of radius 1. However, you want this for all since your z isn't specified, you want this for all z. So essentially, in 3D, what would happen here is that you're in 3 space. Now, of course, in the xy plane, we can imagine that there's this circle that is in the xy plane. So that is, this is a circle in xy plane. However, the same thing must happen at the level of z equals 1. You must have that same circle. And the same thing will happen at z equals a half. And the same thing will happen at z equals minus 1. And so what you'll realize is that you can create this, you'll end up with a cylinder running in both directions. I don't know, that's probably not gonna. You essentially create an object that's a cylinder. So it's 2D, it's hollow. It has 2 dimensions. Flat. So it's a 2D surface, and whose cross section are circles of radius 1. Above your x squared plus y squared equals 1. So it's like a tube or a pipe. We call this guy a cylinder. And we'll talk about cylinders more. This is a circular cylinder. And we'll talk about cylinders more generally next time, but this one is specified. So essentially we have a circle, but we want it to run along the z-axis because it should work for all z. And so, yeah, so this guy in 3D is not a circle. He's actually a cylinder, which is a 2D surface that is a single shape propagated along an axis. We'll call that a cylinder. By the way, just following up, question here. How would you describe a circle? Round, mathematically. A cross-section of a cylinder, equation-wise. Let's say the circle x squared plus y squared equals 1 in the xy plane. How would I describe that circle? So I'm talking about the one that specifically lives in the xy plane. That guy specifically. So what is the cross section of that cylinder that lives in the xy plane? How could you describe that with equations? No. No, here's how you would do it. You would kind of cheat. You would need two equations to describe this. What you would say is, say x squared plus y squared equals 1, and comma, meaning and, force your z equals 0. So what you would do is you would need two equations. Now, a follow-up question would be, is there a better way? And to that, I would say, stay tuned. Of course, there's a better way. We'll talk about it later. There has to be a better way. There has to, right? I don't want to talk about this one thing by using two equations. I need a pair of equations to describe the same thing. But again, by me actually saying that should start to give you guys an idea of how that was beyond your brain walls. It should start to give you guys some idea. I just said I needed a pair of equations to describe this one object, kind of hearkening back to something where we spoke about something having several equations. But we'll move on there. Parametrics, yeah, David has been paying attention. Parametric curves are actually going to give us a very efficient way to talk about curves in 3 space. I will kind of leave it at that. We'll get back to this soon. But yeah, something like this is actually a cylinder. We'll talk more about those in the future. Now let's talk about distances in 3 space. It turns out the same way we measured distance in 2 space, the same idea can work. Essentially, the idea is if you're in 3 space, and I wanted to say I'm at this point and I want to measure the distance d connecting that point, what I can do is I can form like this right triangle and use Pythagoras' theorem to measure this guy. And so essentially the same thing how you prove to find distances in 2 space. can work with 3 space. So yeah, the distance formula applies. It's the square root of final x minus initial x all squared plus final y minus initial y all squared plus final z minus initial z all squared. You kind of just extend the distance formula. Now, in 2D, of course, if you have x1, y1, and x2, y2, then the distance between them is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And notice what happened here in 3 space. You kind of just added a z component to that. Whenever you do something like that, whenever something follows, so it's similar to just add z. Just add water. Okay, just add z, and you get this new formula. Whenever something like that happens, we say that it generalizes naturally, meaning you can just add another similar component to your formula, and it will work out. This, by the way, will work out in higher than 3 dimensions. So if I'm in 4th dimensional space where I have 4 coordinates, how would I measure the distance between 2 4 coordinate objects? Well, just the square root of the sum of the squares of the 4 components. So that is, yeah, generalizes very naturally. That being said, it also follows very naturally. Let's do a proposition here. The equation of the sphere with this center and radius r is given by that. So I had a few people mentioning equations that looked like this before. This is going to be the equation of a sphere. And why is that? Well, if the center is HKL and all points around on the surface of the sphere, let's say this is described by x, y, z, it means that the distance between these 2 points is always going to be r. So essentially what you would have here, the distance between x, y, z, and HKL is r. That means if I take the square root of x minus h squared plus y minus k squared plus z minus l squared, and I take the square root of that, that is going to be r. And then square both sides. This gives you what we call the equation of a sphere. So this is the equation of a sphere in 3 space. And by the way, the equation of a sphere in n space is going to be very similar to that. It generalizes naturally. Let's put nice add to last name. So that's the equation of a sphere. Let's just do a simple example here. Yeah, distance measured in 4 dimensions, you just add another component. Of course, you wouldn't Hello? Are you guys still here? Class is not canceled. I am back. Okay, yeah, been dealing with this all day. So, okay, so you guys can hear me? Oh, so, I mean, you guys had time to finish the problem, so this is good. So what's the answer? Yes, and now, okay, so yeah, let's just actually jump back into, so annoyed with this thing now. Essentially, you'd complete a square. So move everything to one side, x squared. I'd move over the 4x plus y squared, move over the 2y, move over the z squared. Then I'm going to complete the square. So for the x, I have to add, well, half that coefficient and square it. For the y, I would have to add half the coefficient of y and square it. Of course, it's an equation, so I have to do this to both sides. Yes, completing the square is a big deal. It'll always be a big deal. Then these three guys becomes a complete square. So this guy is just x, and the guy on the inside here, minus 2, all squared, plus it's y, and the guy on the inside here, y plus 1, all squared, plus, of course, this is z minus 0, all squared. And on this side here, we have 5, which I can think of as radical 5 squared. So this is a sphere with center 2, minus 1, 0, and radius square root of 5. So that is actually a sphere. Right. So this is supposed to be the center. Remember, it has to be x minus blah. So if you go to the general formula, which is here, you have a negatives here. So this y plus 1, you want to think of it as y minus. You want to think of it as y minus a minus 1. Okay. And so that is that's your sphere. Okay, what else? Let's talk about regions in 3 space. So we looked at spheres. It's a very important idea, believe it or not, knowing about spheres. And let's talk more about generally regions. Now, we know about regions in R2, so I had an R2 example here. Let's sketch the region y is less than x in R2. What would that guy look like? Well, so this is x, and this is y. And essentially, if you look at y, essentially you'd look at y equals x, which is this line. Yeah. So this here is the line y equals x. And pretty much you want all the y values that are below this line. So you want all outputs to be less than y equals x. And so that is this region here. Oh. Make this a little bit thicker. There we go. So this entire region here below this line represents the region y is, so this is the region y is less than or equal to x. Above here, y is greater than or equal to x. You'll notice here, like for example, you would have the coordinates, say 1, 0. Your y coordinate is less than or equal to the x coordinate. Whereas up here, you'd have the coordinate 0, 1, where your y is actually greater than the x coordinate. So down here is this region that we want. Now, being able to find regions in space is also going to be very important. Correct. So as someone mentioned, I have a line here in bold because it includes the line because it's less than or equal to. If I were to actually look at something like y to be strictly less than x, then what you would have is you would draw a broken line to denote that it does not include the line y. So this is y equals x. Does not include. But the region would, other than that, be the same region. So you'd think of it as this guy below here. Okay, so that's how you can think of this region in 2D. Now let's talk about some regions in 3D. Yay! Yay! Okay. So what do you guys think that this region is going to look like? The region x squared plus y squared plus z squared is less than or equal to 1 in the first octant. You messed you up in your algebra test. Yeah, throwback, right? Let's actually go back to the nostalgia and let's give it some crack. We're in 3 dimensions. So here's one thing. Now, do you see the same when I was up here, how I figured out where, yes, it's going to be an eighth of a sphere. How did I figure out where the region y less than or equal to x is? The first thing I did was I pretended it was an equal sign and I drew that. Then I realized what part of space that I wanted that would satisfy the inequality. In the same way, I'm going to do that here. So pretty much what I do is first pretend it's an equal. So first, I would sketch x squared plus y squared plus z squared equals 1. Now we all know that that is an equation of a sphere. That is called the unit sphere, in fact. And So here, to give you guys a drawing lesson. So first, you draw the axes. Ugh, so used to writing X and Y. Jeez. This happens when you haven't taught Calc 3 in a long time. Just used to. Okay. So the first thing you're going to do is I would actually draw a sphere. Okay. Now, color here. So I would draw right, and then there's the okay. So I draw the entire sphere. Okay. Now what I do is now hopefully you guys can. So how you draw a sphere is basically draw a big circle and then just draw something that goes around the equator of that circle. And in 3D, that kind of looks like a sphere. Can everyone do that? You really want to practice drawing in 3D. It's going to be something that's going to, especially in the next class, is going to be very necessary. Now what you kind of do is you kind of carve out what you want. Now the first octant I know is this me standing in the first room here. Yeah, and I'm on a tablet. I'm actually quite proud of myself here. Now you kind of carve out what you want. You only want this 1/8 of the sphere that's in this first room. So pretty much it's going to be the part of the sphere that's cutting out here. So there's going to be that line. It's going to cut into when x equals 1, when z equals 1. Then there's going to be a part that comes down here where y equals 1, and then it's going to come around here. So pretty much you would have this up part here, but I probably should have been the lighter one down there. You have this filled in chord here. So if you were to look at it from, say, a different angle, so you pretty much have this guy. Right? So on this side, you would have, this is the XZ plane. And behind here, you would have the YZ plane. And on the floor, you'd have the XY plane. And you are actually filling in everything in here. So the actual drawing is this part here. The actual object you want is this guy. Boom. 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 Okay. So that's the part of the sphere that you want. And that's describing this region. This is a region that you guys will become very familiar with over time, but that's the idea. So what you do is you first draw the full object, and then you can slice off the part of it you want. That being said, what do you think this region would look like? sketch this region. And we also have the requirement that your y should be less than or equal to 0. Your z should be greater than or equal to 0. It's in R3. I don't know what's painful in terms of bounds mean. It's a little painful in terms of bounds. What do you mean? More than painful. Yeah. What do you think this is going to look like? Spheres? No, these guys are not circles. We're in 3 dimensions and there are 3 variables here. Okay, so follow along, children. Try to actually sketch this yourself. Don't just watch me. So we have, I'm on a tablet. It's much easier to do this on paper. So we have that. That's our x. That's our y. That's our z. Now, if you look at 1, x squared plus y squared plus z squared equals 1, that is a sphere. That is in fact a sphere of radius. That is a sphere of radius 1. So that's going to be this guy. Right? Then there is another guy. There's another sphere. And its radius is 2. So we have a sphere of radius 1 and a sphere of radius 2. Now, of course, for the y to be less than 0, it means I want it towards the, because it's the square root of 4. So the 2 came from the square root of 4. Right, so this is like I have x squared plus y squared plus z squared equals 1, more specifically greater than or equal to 1. And I have x squared plus y squared plus z squared less than or equal to 4, which is 2 squared. So this here hits at 1, this here hits at 2. Now what I'm going to do is this cuts where y is less than or equal to 0, so I want that side. Also, my z needs to be greater than or equal to 0, which means I want on top. So I want behind here and above the xy plane at the same time. So now what I'm going to do is I'm going to start drawing that in. That means I'm going to have this part here. And this, so let's say the negative x-axis goes that way. Negative y-axis goes that way. Negative z-axis goes that way. So this is going to come down wherever that point meets. That's the inner one. Then I'm going to have the other one coming down like here, hitting that. And it actually touches this over here. It's that. So I have this. Then this part here is going in there. And then this comes down. Ugh. And so the object we want is that object. So you have, boom. Now this needs to be a little bit rounded. Boom. 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 And that is our figure, ladies and gentlemen. Of course, not drawn to scale because I suck at drawing on a tablet. And I guess you could think of it as an avocado. Like some people said, amphitheater avocado. Yes, millennials. So that is actually the object. It's kind of like those pictures of an igloo that you would see. But as you can see, it's the region in between two spheres such that the y coordinates are all negative, but the z coordinates are all positive. So yeah, it's as if you had a very spherical avocado. You took out the seed and you slice off the two octants off of it. And those are the guys you actually care about. So what I did was I drew, again, the two spheres. And then from that, I sliced off the pieces that I want, threw away the pieces that I don't want. Yeah, it's like the quarter of a coconut. We're not wasting food. This is the part that I'm going to eat now. I put the other 3/4 of the coconut in the fridge and we'll eat it later. So we don't waste food around here. But that is the region. Now, hopefully you guys, so you would draw this, of course, it would look, I don't know if I want to risk this again. Looking at something else. Okay, never mind, I give up. Okay, so that's how you'd sketch it by hand. And when it comes to the next class, you're going to need to be able to sketch things in 3D very, very well, because you're going to need to do it very quickly. When it comes to just setting the problem up, you're going to need to be able to sketch something in 3D, and then you're going to do integration. And you're going to do all sorts of things, but it's often going to be the case. You need to first visualize it in 3D, seeing what you're dealing with, and it will inform your calculations. So knowing how to draw regions is going to be very important. This kind of a follow-up here just to see who was paying attention last time we did polar coordinates. Can you describe this region using simpler inequalities? So this is the region. How would you describe that in, say, I actually forgot polar coordinates. Need to remember. It's what I'll say is undo. Go back to 2. Think about it. We'll move on. So yeah, and that's pretty much the 3D coordinate system. So pretty much think of it as you being in a room. These are the coordinate planes. We know how to find positions in here using the rectangular coordinate system. It's also worthy to mention that a lot of these equations that we remember from 2-space that have certain shapes, they mean different things. So while this guy is the equation of a circle in 2 dimensions, it's actually a cylinder in 3 dimensions, and that's something that you're going to need to be aware of moving forward. Here's how we can find distances between points. Here is the equation of a sphere. That's going to be important. Here is how we can sketch regions. What's the standard form in 3-space? What do you mean? Oh, that's actually a loaded question, but yes, if you're thinking, there is a theta that exists in the xy plane just as before, and you'd start from the positive x-axis. But in terms of angles, there are going to be several that you'd have to worry about in the 3-dimensional case. So we'll save that for another time, probably the next class. Right. So yeah, so hopefully that kind of gets you used to the idea of working in 3 dimensions and how you would go about sketching stuff. What happened here? What the heck was that? Plane. Yes, polar coordinates is r and theta, but of course here you'd have a comma z. So this means I'm describing coordinates in r comma theta comma z, which by the way, in 3-space, this is called cylindrical coordinates. Okay. But think about how you might describe this in quote unquote cylindrical coordinates. It's a little bit above our pay grade, but I'd like you guys to start actually thinking about it. Yeah, so that is just getting you used to the 3D space. It's not really a 3D coordinate system. We only spoke about one coordinate system here, the rectangular coordinate system. There are others. There's a cylindrical coordinate system where you kind of combine polar coordinates with 3-space. And then there's another popular coordinate system called the spherical coordinate system, which is kind of like it's a whole other thing. But let's actually move on. Now, one thing when it comes to actually describing things in 3 dimensions and higher, vectors become very indispensable, as I call them here. So what I want, is that misspelled? What I want to talk about now is vectors. And we're going to do some basics, and then I'm actually going to combine 3-space with vectors, and then I'm going to talk about how we can describe curves using vectors and a lot of nice things. Vectors, super important when it comes to 3 dimensions and higher. And of course, they do have a lot of applications in 2 dimensions as well, but we are kind of I see someone actually guessed the thing. Yeah, you are incorrect in the Z component, but otherwise you're fine. So think about it for another time. Right now, I want to just run through some basics of vectors. So A lot of you have seen this before, so this is going to be a review for a lot of you. But let's actually jump into it. So a vector is a quantity having both magnitude and direction, and it's kind of going to seem disjointed from the things I was talking about earlier in section 12.1, but this is really all connected. Vectors are very efficient in describing things in 3 dimensions. So we really want to go back to basics, learn about vectors so that we'll be able to use them. A quantity having both magnitude and direction we call a vector, quote unquote. Now, this is not a vector in the abstract sense. This is a vector more in the physics sense and in the calculus 3 sense. And it means a vector, quote unquote, means something in higher mathematics. But for now, this is the guy that we are going to actually talk about. A vector is a quantity having both magnitude and direction. Geometrically, we represent this by an arrow or a directed line segment, like so. Why am I still in green? Yeah, you literally write an arrow. That is a vector. That's basically it. So now, when it comes to a vector, the tail, or the point where you start the vector, this is called the initial point of the vector. Where the arrowhead ends up, this is called the terminal point. Or sometimes we call it the final point. And so the magnitude is just the length of the vector here. So this is the magnitude. It's represented by the magnitude, or length is represented by how long you draw the arrow. So yeah, this is the picture of a vector. It's like just an arrow with a directed line segment. Okay. So I just described to you the final point, initial point. So the final point is where the arrowhead ends up. And this is kind of indicating the direction in which this guy is pointing. Now we're going to talk about how to illustrate, quantify direction pretty soon. But for now, just know that that's a vector. I can draw an arrow and that's a vector, okay? Now we can name vectors based on their initial and final points, and we can use letters. Now, if I have a initial point A and the final point is B, then I might call the vector AB with a little arrow over it. Now, I don't know if you guys can actually see that very well. Maybe I can make this a little bit larger. Right, so here you see like this arrow over it, okay? So what that would mean is that, yeah, if I'm in 3 space or something, for example, so let's say, here's my X, here's my Y. Here's my X, here's my Z, here's my Y, and here is a point A, and over here is a point B, then this is the vector AB with an arrow over it. Or you might give it another name, like little a with an arrow over it. So vectors are usually represented by either putting an arrow over it, which normally if you're writing it by hand, that's how you do it. Or in textbooks, it would be bold. Yes, old habits die hard. This is in fact true. This is why practice is important for mathematics. You really want to be like, by the time you're in an exam or something, like almost on autopilot. We'll talk about that some other time. But yeah, that's how you'd think of a vector, right? Now, when it comes to equality and position of vectors, 2 vectors are considered equal if they have the same magnitude and direction. They do not have to have the same initial point. So if I have a vector that goes like that and another vector that goes like that, now if I realize that this guy has an angle of 45 degrees here, and the length is, say, 2, then in some other region of space, if I draw a vector of 45 degrees and the length being 2, these guys are considered the same vector. Right? So even if in 2 space, let's say here's my y-axis and here's my x-axis, I can have 2 vectors in 2 different positions, but as long as they have the same direction and they have the same length, they're considered to be the same vector. Okay, so vectors are equal if they have the same magnitude and direction. They don't have to have the same starting points and ending points. Okay, so I mean, here I put length 2. Okay, so we consider these two. The position of the vector in most cases actually does not matter. Sometimes though, it is necessary for us to have some common reference point for some vectors, and the origin of n space is often going to be this point. And whenever we want to emphasize that a vector has initial point, the origin, we call it a position vector. So that is going to be a name that we will give things. So here, let's make sure everything. So let's say I'm in the XY plane. So I might have a vector. This is called the vector A. If I were to move that same vector, then I would call it the position vector A. Okay, so with a position vector, the only thing that makes a vector a position vector is that the initial point is the origin. That's the only difference, right? But it's the same vector that I can just move. Once you move it so that the initial point is the origin, we call it a position vector. And position vectors are insanely useful. We are going to use them all over the place to do some very, very important things. For example, like describing equations of curves and equations of surfaces and equations of solid objects in n space. We're going to need to use position vectors to actually get this done. So yeah, that's it. Now, when it comes to mathematical notation of vectors, one thing we can do is actually to say, okay, if you have a position vector, so let me just emphasize position vector, whose terminal point is A1, A2, we denote this vector in the following way. So this is like saying, okay, so let's say in 2 dimensions, here is my x, here is my y. This is the point A1, A2. Then the vector that starts at the origin and hits that point, I call that angled brackets A1, A2. That is the notation. I can call that vector A. So once you see me put this angled bracket here, it means I'm not necessarily thinking of A1, A2 as a point. I'm thinking of it specifically as a vector. There are many situations in which a point and a vector, we're going to think of them as interchangeable, but there are also many situations in which they are not interchangeable. So it's very important in Calculus 3 that when you intend to think of something as a vector, that you write angled brackets, not parentheses. Okay, now in 3 dimensions, a very similar thing happens. You write angled brackets. So this guy here, this is just, this is the point A1, A2, whereas this is the vector A1, A2, right? So this is something that has magnitude and direction. This is just something that's a location, a specific point in space, okay? So whenever we use angled brackets, it means that we are considering a vector that starts at the origin and hits the coordinate a1 comma a2 or so on. And it extends very naturally for n dimensions, but we're not really going to be talking about that a lot. Now, when it comes to these things, in general, in n, we call the numbers in the ith position the ith component. But of course, if we're in R2 or R3, we call 1 the x component. We call 2 the y component, and we call 3 the z component for the vector 1, 2, 3. And I just said, here's a sketch of the vector. So I wanted to sketch it for you guys. So that's pretty much, so we know how to find the point 1, 2, 3. So you go 1, then you go 2, then you go up by 3. Now, if you have a vector that goes from the origin, hitting that point, that vector is the vector 1, 2, 3 with angled brackets, right? So the guy that starts at the origin and hits that point 1, 2, 3. So this is the coordinate 1, 2, 3. The arrow that starts at the origin hits that is the angled, it's an angled coordinate 1, 2, 3, which is the vector 1, 2, 3. So that's what that picture would actually look like. Okay, so that's all a vector is. Now, in general, they can float anywhere in space as long as its magnitude and direction is the same. It's the same vector. But position vectors, guys, where their initial point is fixed at the origin, these are very important. And you pretty much just figure out that the initial point is going to be the origin. The final point is going to be the coordinate that's described by the components. Moving on. Sometimes you want to be able to find a vector that actually connects 2 points. And how we actually do that is this final minus initial idea. So, for example, let's say I have 2 points in space, right? So this is in 3 space. I'm not going to draw the axes, but here's a point 4 comma minus 2 comma 0. And somewhere else in space, there is a point 1 comma 3 comma 5. And I want to talk about the vector that starts here and ends here. How would I actually fit that vector? So let's say that vector, I want to call it A. Then I could actually write the components, A component notation by this here is the final point. This here is the initial point. I'm going to take the final components minus the initial components. So it's 1 minus 4, comma, 3 minus a minus 2, comma, 5 minus 0. So the vector that connects those 2 coordinates will be the vector minus 3, comma, positive 5, comma, positive 5. Any questions on that? Okay, so we're good. So for some people it's a review, but let's keep moving on. Now, when it comes to actually finding the length of the vector, so remember, a vector is something that has magnitude and direction. The literal length of the arrow, I would correspond to a magnitude, okay? Now, how do you actually find that? Well, it's kind of the length from this point to that point, right? The length between the initial point and the final point, that is actually going to be the length of the vector. And so what we can do is use the distance formula. So if I have a vector a1, a2, a3, then the magnitude, which this is the notation here, we use either single absolute values or double absolute values if I want to emphasize that I'm thinking of this as a vector, but really they're totally interchangeable. It's the square root of the sum of the square of the components. And one way you can think about this is that it's a position vector where you want to find the distance between 0, 0, 0 and the point A1, A2, A3. Yeah, double absolute values is optional. So if I wanted to find the length of this vector, then it's really absolute. Yeah, no, when it's just absolute values in higher than 1 dimension, you think of it as this formula, okay? And so if we apply the distance formula, apply distance formula that we covered in the last section, we get, well, that formula right there. So for example, find the length of the vector in the example above. So the vector that connected this point to that point, final minus initial, is how you would create that vector. So our vector A from the previous example was -3, comma 5, comma 5. Now, if I wanted to know, if I were to draw this vector and find the length, how long is it, then I'd be able to say that the magnitude of this vector is going to be the square root of -3 squared. Now, it doesn't even matter that I put the minus, 5 squared plus 5 squared. Now, of course, that is going to be the square root of 59. Okay. And that's it. This is the length of that vector. Okay, it's another thing. Something else I want to remind you guys of is operations on vectors. We can combine vectors and we can scale them and we can do all sorts of things. Two main operations are called the addition operation, and we have what's called the scalar multiplication operation. Okay. Now, component-wise, we can add two vectors by adding their components, and we can form what's called the scalar multiplication of. Yes, we are going to be doing dot and cross product, but that's in another section. And we can talk about the scalar multiplication of two vectors, where we can multiply by a scalar. Now, as I mentioned way up here, but I typed it, but I didn't mention. There are two types of quantities we're always want to pay attention which kind of quantity we're looking at. Once I now introduce vector, I want you to think of things that are not vectors, quantities that are not vectors. Quantities that only have magnitude, we call them scalars. So a vector is a quantity that has magnitude and direction. If we only have magnitude, and it could be positive or negative magnitude, we call these guys scalars. Okay. Now, scalars for us is really just going to be real numbers. So if I have two vectors here, these should be angled parentheses. And C is a scalar, then the operations addition and scalar multiplication can be described notation-wise this way. If C is greater than 0, then if I take C times a vector, it has the same direction as that vector. If C is less than 0, it gives me the opposite direction. If C is equal to 0, I get what's called a zero vector, which is a whole other thing. It's a vector with no direction and all directions simultaneously. And the length of this is just the magnitude of the scalar times the magnitude of the vector. And the sum of these vectors, a phrase that's sometimes called, is the resultant vector. So what does this actually mean geometrically? So let's say I have a vector A, right? And I also have a vector B. Then if I were to look at the vector A plus B, what is that? Well, it's like I take the vector A, and then to its head, I attach the tail of B. And the quote unquote resultant vector is the vector that has the tail of A and the terminal point of B. So it starts where A starts and it ends where B ends. And this is the vector A plus B, right? So this is sometimes referred to as the resultant vector. That's especially a terminology that we use in physics. So we can add vectors to each other. Geometrically, this means you just attach them from tail to head, tail to head. Computationally, you literally will add their components, okay? Now, if I have, as indicated what I mentioned here, if I multiply a vector by a number, it actually scales it. So let's say here I have a vector. Let's say here I have a vector. Let's say here I have a vector A, which is this guy. Then if I were to take 2A, essentially what that is its same direction, but the length is stretched by a factor of 2. So if this length here was L, then this length here is 2L. If I were to take the vector minus 2A, it's going to be like 2A, but literally in the opposite direction, right? Similarly, minus A would just be the vector A, but in the opposite direction. So the final and the initial points switch positions, okay? So when you multiply a vector by a number, it will scale it. Now, if you take, say, 0 times there, this gives you what's called a 0 vector, and this guy has no picant. He's a vector that has no direction and all directions simultaneously. And later on, we'll actually talk about what that might mean in terms of computations. But a vector is something that has magnitude and direction. I can kind of write it down notation-wise as a coordinate with angled brackets instead of parentheses. Whenever I do that, it's normally customary to think of it as a position vector, where but even not. This is just, a position vector is one where the initial point is the origin. Now, I can find a vector that connects 2 points by taking the final point minus the initial point. I can find the magnitude using the distance formula, and I can add 2 vectors together just by adding the components. I can scale a vector just by multiplying them by scalars, which in this case 2 is called the scalar. In this case, 2 is called the scalar here. And we pretty much just think of it as how we're scaling this vector, how we're stretching or compressing the vector. If you multiply by a negative number, it switches the direction to the exact opposite. Literally, you do a 180 degrees. This also leads to a convention of subtracting vectors, which we can, component-wise, we actually subtract the components. Geometrically, what we can think of this as is just adding the negative of the vector. So for example, if I have a vector here, A, which is like that guy, I have a vector B, which is, say, this guy, then of course, minus B is going to be that guy. And so if I were to look at the vector A minus B, what that would look like is A plus minus B. And so that's like me taking, so let's actually, so that's like me taking A and then attaching to its tail minus B. And then this vector here that connects from the tail of A, this is the vector A minus B. Okay. So over here we have minus b, and over here we have a. So if I take a and subtract b, which means I take b but literally go in the opposite direction, that is how I would find the vector a minus b. Two vectors are parallel if they are scalar multiples of each other. So i.e. a and something like ca are parallel. So for example, if I have a, which is this vector, and I have 2a, which is just the same direction, but just a little bit longer, or I have minus 2a, which is opposite direction, these are all parallel. And computationally speaking, these are the algebraic properties that a vectors will actually obey. Now, am I forgetting anything? We're kind of running, I'm pretty sure, I mean, we started a little bit late, but I'm pretty sure we're over time at this point. What I would like you guys to do is to actually you know what? Let's actually. Do I have? Let's run through this example and then we'll end there. Okay. Just to deal with vectors computationally. So we'll deal with the geometric way of dealing with vectors a little bit later. But let's look at the computational ways of dealing with vectors. So here I have two vectors, the vector 1, 2, 3, and the vector minus 4, 0, 5. I want to compute the magnitude of a plus b, a minus b, 2a, 3b, and 2a minus 3b. And I want to actually compute them. So let's just run through this quickly. The magnitude of a is going to be the square root of the sum of the components. That's just using the formula. This is 1 plus 4 plus 9. So that's 9 plus 5. This is radical 14. B. If I want to talk about a plus b, well, this just means I'm taking the vector 1, 2, 3, and I'm adding to it the vector minus 4, 0, 5. Now, in general, you don't have to write this, but I'm going to write it out. What you do is you just add the corresponding components. Now, normally you don't have to actually write that out, but essentially you'll end up with the vector minus 3, comma 2, comma 8. So that would be a plus b. A minus b. If you want to find the vector a minus b, computationally, this is just 1, 2, 3, minus 4, 0, 5. This is going to be 1 minus a minus 4, 2 minus 0, 3 minus 5. 5, 2, minus 2. If we want to talk about 2a, well, this is just 2 times 1, 2, 3. 2, 4, 6 by our definition. So don't have to write this out, but it's really just 2 times 1 plus 2 times 2 plus 2 times 3. You can just distribute the scalar multiple across all the components. 3b. Look at 3b. This is just 3 times minus 4, comma 0, comma 5. That was our b, right? Yeah, so that's just going to be minus 12, 0, 15. And again, didn't really show it, but this is 3 times minus 4, 3 times 0, 3 times 5. And then if I were to ask, what is 2a minus 3b? What vector is that? Well, this is 2 times 1, 2, 3, minus 3 times minus 4, 0, 5. This is going to be 2, 4, 6, minus 12, 0, 15. So this is going to be 2 plus 12, 4 minus 0, and 6 minus 15. And so you can create all these vectors. Hopefully that was clear. And again, I kind of rushed through things here, but because I kind of expect a lot of you guys to have seen vectors before. I wrote down a lot of notes here, which you can read through slowly in case you want to jog your memory and you don't actually remember a lot about vectors, but kind of rushing through the first few important ideas. Hopefully everyone followed. Did I lose anyone? I don't know. Okay, so good. So we'll pick up next time talking about some more important things. These guys down here. Yeah, I heard some people leaving. We're actually over time, so they probably had to go. But I will post the notes, and we'll pick up with this on Monday. So some of you said you forgot about polar coordinates. Be sure to review that. And parametric equations, be sure to review that. Those are all coming back. We're going to need those. And we will actually pick up. Let's wrap this up. Yeah, I don't know where they had to go, but so a few people left. Maybe they're just bored with vectors. So yes, we're going to have 2 exams and the final. I will give you full instructions on Monday how we're going to do the exams, because I'm just going to do my own thing. I can't wait on the math department anymore. Exam 1 will cover everything up to series, everything that we did from the beginning of the class right up to series. Exam 2 will cover everything after that. Essentially is how it's going to work out. On Monday, I'll let you know how it's going to be administered, and I'll also give you the practice test. Yeah, I think it's around 10.10. The last section in series is the end of exam 1. So read up on 3D space, read up on vectors, review polar coordinates, and we will pick up with those things on Monday. I'll probably quickly go over these because I don't know. I feel like I was going fast, but I'm not sure. You guys seem to all be following. But yeah. Lots of technical difficulties today, but we survived. We made it through. And yeah. So that is it. Thanks for attending, and hopefully you guys are still safe, and I will catch you guys on Monday with a lot of information, and we will stop there. So bye everybody.